Hello everyone! In this control theory, mobile robotics and estimation tutorial, we explain how to develop and implement an extended Kalman filter algorithm for localization of mobile robots. Namely, we explain how to use the extended Kalman filter to localize or estimate the robot location and orientation. Location and orientation are called the robot pose. We also explain how to implement the localization algorithm in Python from scratch. Here, we need to immediately state that the localization algorithm is developed under the assumption that the locations of external landmarks, shown over here, are known, and that the landmark measurement correspondence is also known. In our second tutorial series, we will consider the case when the landmark measurement correspondence is not known, and in the third tutorial series, we will consider the case when both the landmark locations and their measurement correspondence are not known. Don't be confused if you currently don't understand what is a landmark or what is a landmark measurement correspondence. These terms will be explained in this tutorial series. Due to the objective complexity of the estimation and localization problems, we split this tutorial series into three parts. Part 1, you're currently watching the first part. In this part, we clearly explain the problem formulation. We explain what is a localization problem. We then explain what are landmarks or markers, shown over here. And we explain the difference between localization with the known landmarks and localization with unknown landmarks. We then summarize the mobile robot model used for localization, and we summarize the odometry model. We then introduce the measurement model that provides us with information about the robot's location with respect to the known landmarks. In part 2, on the basis of the problem formulation given in the first part, we explain how to mathematically solve the robot localization problem by using the extended Kalman filter. We thoroughly explain how to compute all the partial derivatives necessary to implement the extended Kalman filter. In part 3 of this tutorial series, we explain how to implement the extended Kalman filter for mobile robot localization in Python from scratch. But before I start with explanations, I need to mention the following. It took me a significant amount of time, energy, and planning to create this completely free video tutorial, as well as almost 500 free video tutorials that you can find on my YouTube channel. And consequently, I kindly ask you to press the like and subscribe buttons. Thanks a lot. Okay, let's start with explanations. In this tutorial series, in order not to blur the main ideas of robotic localization with too complex mobile robot models, we use a differential drive robot as our mobile robot. A sketch of a differential drive mobile robot is shown over here. This is done since a differential drive robot has a relatively simple configuration or actuation mechanism which results in a simple kinematics model. The main purpose of this tutorial is to explain the main principles and ideas of robot localization without blurring the main ideas with complex robotic configurations or complex mathematical models. Of course, everything explained in this tutorial series can be generalized to more complex mobile robot configurations and even to UAVs or autonomous driving vehicles. We thoroughly explained the model of a differential drive robot in our previous tutorial, whose link will be given in the description below this video. However, for completeness of this video tutorial, we will briefly summarize the model, and by using this model as well as the odometry model, we derive the state equation for localization. Capital X and capital Y is the fixed inertial coordinate system. This coordinate system is also called the inertial frame. Capital XB and capital YB is the body coordinate system. This coordinate system is also called the body frame. The origin of this coordinate system is at the point B, shown over here, which is located at the center of the mass or the center of the symmetry of the mobile robot. The body frame is rigidly attached to the robot body and it moves That is, it translates and rotates with the robot body. Lowercase x and lowercase y are the x and y coordinates of the origin of the body frame. That is, the coordinates of the point B. These are the coordinates of the center of the body frame in the inertial coordinate system. This is very important to understand, that x and y are represented with respect to the inertial coordinate system. The angle theta or theta, however you like to pronounce it, is the angle that the x-axis of the inertial frame makes with the xb axis of the body frame. This angle is called the orientation angle. The symbol v denotes the instantaneous velocity of the body frame origin B. The symbol omega denotes the instantaneous angular velocity of the mobile robot. As explained in our previous tutorial, whose link is given in the description below this video, by discretizing the continuous time kinematics of the mobile robot, we obtain the discrete time model represented by this set of equations. In these equations, the subscript k is the discrete time instant. Xk and Yk are the x and y coordinates at the discrete time instant k. That is, x with the subscript k is actually x at the time instant k times h, and y with the subscript k is y at the time instant k times h, where h is the discretization constant. That is, h is the time interval between the time instant k and the time instant k plus 1. These quantities are shown over here. Sk, and shown over here, is the distance traveled by the robot between the time instant k and the time instant k plus 1. This distance is actually in the direction of the instantaneous velocity vk. Vk is assumed to be constant between the time instant k and the time instant k plus 1. Theta k is the orientation at the discrete time instant k. Delta theta k is the change of the orientation between the discrete time instant k and the discrete time instant k plus 1. Theta k plus 1 is the orientation of the robot body at the discrete time instant k plus 1. The model given over here describes how does xk, yk, and theta k change in time. Here, for simplicity, we assume that by using the odometry system, the following two quantities are directly measured. First of all, we assume that Sk is directly measured. Then, we assume that the change of the angle delta theta k is also measured. Instead of these two assumptions, we can also assume that the velocity and the angular velocity of the mobile robot are directly measured. Here, we need to explain the odometry process. We can measure the distance traveled between the time instant k and k plus 1, that is, we can measure Sk by using wheel encoders or some other method. We can measure the angle change delta theta k by using a gyroscope or a compass. However, due to the measurement imperfections and due to the other mechanical phenomena, such as, for example, wheel slipping, we are not able to accurately measure both Sk and delta theta k. Instead, we measure their corrupted version denoted with the superscript tilde. That is, instead of measuring Sk, we actually measure Sk tilde. And Sk tilde is actually true Sk, that is true distance that's traveled between k and k plus 1, plus this noise term over here. Similarly, we don't measure the true value of delta theta k. Instead, we measure its corrupted version, delta theta k tilde, and delta k tilde is equal to delta theta k plus this noise term. We assume that both nsk, that is this noise term, and n theta k, that is this noise term, are normally distributed with the standard deviations of sigma s, and sigma theta. From this equation, we can express the true values of sk and delta theta k like this. Next, we can substitute these two equations in our kinematics model given over here. And as the result, we obtain this important equation. We can transform these equations by separating noise from the states and measurements in this set of equations, and consequently, by just expanding these two terms, we obtain this set of equations. Next, we formally define the states and inputs. The states are defined like this. The state z1 at the time instant k is simply equal to xk. Then the state z2 at the time instant k is equal to yk, and the state z3k is simply equal to theta k. The state vector is defined like this. Next, we need to define the inputs. We define the inputs like this. u1k is actually measurement of sk, that is, u1k is equal to sk tilde. u2k is the measurement of delta theta k, that is, u2k is equal to delta theta k tilde. Here, you should stop for a second and try to understand the following. Over here, we defined actual measurements as inputs. However, people with a strong background in control theory will find this assignment confusing. Usually, inputs in state space models are control variables determined by an algorithm or determined by us. However, here we define inputs as output measurements. That is, inputs are defined as measurements of the travel distance and change of angle. This is a formal assignment that is often used in robotics literature. Also, these inputs are actually only observed at the discrete time instant k plus 1. This should always be kept in mind. By substituting new symbols for states and inputs in our original kinematics model, we obtain this set of equations. Next, for clarity, we shift the time index from k plus 1 to k in this set of equations. As the result, we obtain the final form of the state equation. And here it is. This is the state equation that will be used for the development of the extended Kalman filter in our next tutorial. Here, it's very important to keep in mind the following when dealing with this state space model. The measurement noise of the measured distance and change of angle formally act as process disturbance in this set of equations. That is, when developing a state estimator, it should always be kept in mind that the stochastic part of the state equation, that is, this part over here, involving nsk minus 1 and n theta k minus 1, is not known. However, we know the distribution and standard deviations of these random variables. That is, we know the statistics of nsk and n theta k. These statistics can be estimated from the collected data. Next, we need to define the concept of landmarks and the output equation. Let's start with landmarks. Localization will be formally defined in the next section of this tutorial. However, here, we can briefly say that the localization is the process of estimating the robot pose vector zk by using the available measurement data and the pose estimate from the previous time step. Now, it's a very well-known fact that by only using the measurements of the travel distance and the angle change, or by using the measurements of the velocity and angular velocity, we cannot accurately localize the robot in space. That is, we cannot accurately estimate the robot pose by propagating in time the deterministic part of our kinematic state space model. That is, we cannot accurately localize our robot by only propagating this deterministic part of the state equation and by ignoring this noise. The naive approach is basically to take these measurements, to form these inputs, u1k and u2k, and to simply to propagate this equation in time. The issue over here is that the variance of the estimate will grow. And as the time goes by, our estimate of location and orientation will gradually deteriorate. That is, the variance of the estimation error will grow. That's why we need to introduce additional measurements. That is, we need to introduce a relative measurement of the robot location and its orientation with respect to certain external object that we call a landmark. We need to repeat this important fact. In order to be able to accurately estimate the robot's location and orientation in space, we need to introduce an additional sensor that is capable of measuring the distance and angle between the robot and external objects known as landmarks or markers in the robotics literature. We can define a landmark or a marker as an object or a feature of the environment that is used as a reference for measuring the robot's location. Namely, we assume that a mobile robot is equipped with a sensor that can measure the distance between the robot and the landmark and the angle of the line connecting the robot and the landmark. The distance is denoted by rk over here, and the angle is denoted by alpha k. This is our landmark with the location xl and yl, where xl and yl are the coordinates in the inertial coordinate system. The robot is equipped with a sensor that can measure, number one, distance rk at the discrete time instant k between the origin of the body frame B and the landmark. This distance is called the range. Then, the sensor can measure the angle alpha k at the discrete time instant k. This angle is the angle between the line in the direction of the range, that is this line, and the heading direction of the robot marked by the velocity vk. The angle alpha k is also called the bearing angle or simply bearing. Here we need to make one important assumption. The location xl, yl of every landmark in the inertial coordinate system is known accurately. This assumption will be relaxed in our future tutorials on SLAM. Next, we need to define the measurement equation. From this figure, it follows that the range rk can be expressed like this. xl minus xk is actually this distance. Yl minus yk is actually this distance over here. And by using simple trigonometry, we obtain that rk is the square root of xl minus xk squared plus yl minus yk squared. On the other hand, from the basic geometry, we have that tangents of this angle, that is the angle of theta k plus alpha k, is actually yl minus yk divided by xl minus xk. From this equation, we actually obtain that theta k plus alpha k is tan or arctan 2 of yl minus yk over xl minus xk. From this equation, we can actually obtain this equation. Here, it's very important to keep in mind that tan 2 is actually the two-argument arctangent function. Here, it's very important to use tan 2 instead the ordinary arctangent function. Next, we assume that the measurements of the range rk and the angle alpha k are corrupted by the measurement noise. That is, we assume that the measurement equation is not only rk is equal to the square root, but instead we have this noise term over here. Similarly, for the measurement of alpha k, we have a noise term over here, where The first noise term and the second noise term are normally distributed with zero mean and with the standard deviations of sigma r and sigma alpha respectively. Now, by substituting new symbols for states in these two equations, we obtain these two equations. The set of equations given in 15 represents the measurement model for a single landmark. However, we need to clarify what happens and how the measurement model is defined when we have more than a single landmark. That is, we need to define the landmark correspondence problem. Next, we need to define what is a landmark correspondence problem, and we need to explain why this problem is important for robotic localization. Let us consider this figure. Over here, we can see our mobile robot, and we can see three landmarks: landmark 1, landmark 2, and landmark 3. Let us suppose that we know the locations or coordinates of all three landmarks. Furthermore, let us assume that the robot sensor can detect the range and bearing angles of three landmarks. What the robot receives are three measurements, where every measurement consists of a tuple consisting of a range and bearing angle. For example, our robot can receive in the first measurement r is 0.3, alpha is pi over 6, then r is 0.55, alpha is 2 pi over 3, r is 0.6, and alpha is minus pi over 3. Our sensor almost instantaneously collects these three tuples. However, these measurements are not labeled. Unlabeled means that the measurements are not assigned to the corresponding landmark. That is, if we just analyze raw data, we don't know, for example, this tuple and its origin. Does it come from this landmark, or this landmark? That is, in the case of unlabeled measurements, we don't know the correspondence between the landmarks and measurements, and we cannot form the output equation given over here. This output equation is very important for the development of extended Kalman filter. That is, we cannot implement the extended Kalman filter without knowing the correspondence between landmarks and measurements. Now, we need to assign every measurement tuple to the corresponding landmark, and after that we need to form a single measurement equation for every landmark. To summarize, the landmark correspondence problem is to assign the landmarks to the received measurements, that is, to label the received measurement tuples, where the label denotes the landmark that corresponds to the exact measurement. For example, in the case of this figure, the situation is not so bad, since these landmarks are relatively well separated. Consequently, it is relatively straightforward to conclude that the first tuple corresponds to landmark 1, and we can assign rk1 to be equal to r, that is equal to 0.3, and alpha k1 to equal to pi over 6. Similarly, the second tuple should come from the second landmark, that is from this landmark over here, and consequently rk2 is 0.55 and alpha k2 is 2 pi over 3, and similarly the third tuple comes from landmark number 3. Now, here it's obvious how to assign the labels. However, let's consider this case. What happens over here? We have three landmarks. However, we can observe that landmark 1 is very close to landmark 3. And consequently, we might obtain the following set of tuples. That is, this is the first, second, and the third tuple. Now, it's very difficult over here to kind of label first and the third tuple. Taking into account that the pose of the robot has to be estimated together with determining the landmark correspondence and taking into account that all the measurements, including the robot odometry measurements, are corrupted by the measurement noise, it is difficult to properly assign the landmark labels to first and third measurements. That is, we are not sure how to assign landmark 1 and landmark 3 to these measurements. The correct solution of the landmark correspondence problem is far from trivial, and it will be addressed in our future tutorials. In this tutorial series, we assume that the received measurements are properly labeled. That is, in this tutorial series, we assume that the landmark correspondences are perfectly known. So keep in mind that. And finally, we are ready to define the localization problem for mobile robotics with known landmark correspondence. The problem formulation is illustrated over here. Let us assume that, number 1, there are n fixed landmarks in the environment surrounding the mobile robot. Here we have 3 landmarks. The locations of n landmarks are known in the inertial coordinate frame. That is the location xli and yli of every landmark I, where I goes from 1, 2, 3 until n, is known. Number 3. The mobile robot is equipped with a sensor that can measure the range rki and the bearing angle alpha ki of every landmark. These measurements are represented over here. Then, number 4, the landmark correspondences are perfectly known. Number 5, the robot is equipped with odometry sensors that can measure the travel distance, given over here, and the robot orientation angle, given over here. Then, by using information about odometry readings, tilde sk-1 and delta theta k-1 tilde obtained at the discrete time instant k, then by using information about landmark measurements, that is, these tuples consisting of the range and bearing angle, and these tuples are obtained at the discrete time instant k, and then by using information about the pose estimate computed at the previous discrete time step k-1, that is, hat xk-1, hat yk-1, and hat theta k-1, at the discrete time instant k, estimate the pose of the robot, that is, estimate xk hat, yk hat, and theta k hat. Here are several important comments about this problem formulation. First of all, estimates of the quantities are denoted with the hat notation. That is, the estimate of xk is usually denoted by xk hat. The estimate of yk is usually denoted by yk hat. And the estimate of theta k is usually denoted by theta k hat. Then, the third assumption, that is, this assumption over here that the mobile robot is equipped with a sensor that can measure the range and the bearing angle, can be changed a little bit such that it is more realistic. Namely, a typical sensor can obtain information about rk and alpha k of landmarks that are in the vicinity of that sensor. For example, some low-cost LiDARs have a measurement range of about 10 to 15 meters, and we can obtain the landmark information only if the landmark is in this range. In the next tutorial part, we will investigate the performance of the extended Kalman filter when all the landmarks can be observed at every time instant k, and when only landmarks in a given sensor range can be observed at the given discrete time instant. Okay, that would be all for today. I hope that you liked this video. If you like the videos I'm creating, please press the like and subscribe buttons. Thanks a lot and have a nice day.